We're talking about areas and volumes of similar solids. So that's going to be in 3D in a second. But I want to quickly review what happens in 2D. This is the picture I tend to draw over and over again. And that is if you've got one polygon, or really any figure, it could be circle, could be funky, but let's look at the simplest thing, a 1x1 square. And I'm going to create another square. It's very important that it's just going to be a similar object. It's not going to be elongated like a rectangle. It's going to be another square, and so it's going to be 3 times the side length. So the scale factor is 1 to 3. Or just, you could say the number 3. I'm tripling the lengths. Remember, the scale factor always specifically talks about lengths, not areas, not volumes. And so I'm tripling one side. If I'm going to make it a square still, that means I'm tripling both dimensions. And that means I'm not going to get just 3 times as much area. What I can do is I can draw a little grid, and I can literally just count how many squares are going to be in there. There's going to be 3 in the first row, but I've got 3 rows now. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 7, right? And so the area is a 1 to 9 ratio. And that 9 is a 3 squared because I tripled the number of rows and the number of columns. So really, you can think of it as just I'm tripling 2 different measurements, and that square is telling me, oh, that both of them have an impact. It's going to be 1 to 9. So remember, that's a 2D review, but it's actually going to appear exactly in the 3D story in just a second. But let's think about the 3D story. Let's move this up so you can see it. Let's say we have a little 1x1x1 cube. I'm going to stop doing inches, but let's assume where they're supposed to be inches. Okay. Now I'm going to triple all 3 sides. My marker is not at its best here, I guess. And so that's going to be 3 by 3. So the width, the depth, the height are going to be all 3. Let me see if I have a better marker. And I'm going to do the same kind of thing here. First of all, I'm going to draw inside here. Let me make sure I draw the... So inside here, I'm going to draw just the bottom layer. Well, the bottom layer is this same kind of 3 by 3 grid. Okay. A 3 by 3 grid of cubes, but just to fill out the bottom layer. So that's going to be like this. There's the top of the bottom layer. Well, actually, yeah, these guys go this way. Okay. And like this. So I've got 9s, really this kind of picture, if I see it from above, I can put 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 cubes just in the bottom layer. So that's going to be 9 cubes there, but that's only taking into account the fact that, oops, let me go up a little bit further here. Okay. That's only taking into account the fact that I've tripled the width and the depth, not the height. I've got another layer here, another 3 by 3 grid. That's going to be another 9 cubes in the middle layer here. And then I've got yet another layer, and there's the top of that grid. I've got another 9 cubes here, which is natural. I tripled the width and the depth. So instead of 1 by 1, I've got 3 by 3 or 9 on each row, but I've also tripled the height, so there's going to be 3 rows. All told, it's a 1 to 27 ratio in terms of number of cubes, and that's the volume ratio. And not shockingly, that's 3 cubed. That's why we call multiplying a number by itself 3 times cubic, because of this link to volumes. So we've got, we really just want to, just like we always want to remember this picture in terms of how area works, we want to think of this in terms of volume. Now, so let's summarize that real quick. This is a very general feature. If I have 2 similar solids with scale factor, well, let's say scale ratio, say A to B. So here it was real simple, it was 1 to 3. That was the example. Then the volume ratio is just the cube, A cubed to B cubed. If the A was equal to 1, which is very common, you're just cubing the B. Okay, so a tripling ratio goes into a 27-fold ratio here. Okay, so that volume ratio is a cube. That's exactly the 2D version of the area ratio, an A to B scale factor, turns into an A squared to B squared area ratio. So remember, scale factor is just a synonym for length ratio, and then the area ratio is just going to be A squared to B squared. Very often the A is 1, but not always. It's nice to be flexible with our ratios. Right? So if we had like a cone, and I had another cone, maybe this was like 2 and that was 5, then I would have the A to B, the length ratio is going to be 2 to 5. Then if I'm looking for the volume ratio, it's just going to be 2 cubed to 5 cubed, 8 to 125. And these guys get big. These numbers get big. When you cube numbers, they get big pretty quickly. That's quite a bit more, quite a bit more extreme ratio than just a 2 to 5 ratio. So I want to go back, though. There's another thing we could have done with these cubes. What if I actually care about surface area and not the volume? I don't really want to go inside it into the bulk of the thing. I just want to stay on the surface. Okay, let's look. Here's the surface area. That's pretty easy. They're all 1 by 1 squares, but there's 6 of them. Top, bottom, left, right, front, back, and that's going to be 6. Okay, let's look at the surface area over here. Well, hey, that's exactly 6 copies of exactly this comparison. Like if you look at the front side here and the front side here, it's exactly the same picture. And so there's one front side here with area 1 turned into a front side with area 9, 3 squared. Top with area 1 turned into top with area 9. The whole thing is the 6, that's what's in common, there's 6 faces, times 3 squared. The ratio, it's 6 to 6 times 3 squared, but that's silly. The 6 is in common. In other words, it's 1 to 3 squared. That's exactly this guy, because it's not different. It's just 6 copies on each face of the same exact comparison. And the same story is true in general. If I have, even though I've got a 3-dimensional figure, if what I'm measuring about it is 2-dimensional, the area is fundamentally a 2-dimensional measurement, then the area ratio is just going to be A squared to B squared. Nothing new, just 2-dimensional calculations put into a 3-dimensional setting. Okay, so if I've got the scale ratio, in other words, that's about the lengths. If that's A to B, the area ratio squares it, the volume ratio cubes it. And we already have a hint of this from the units we use. We would use like inches here, we would use cubic inches here, we would use square inches here. It turns out that those units really are fundamentally keeping track of these ratios in the right way. Okay, although you don't usually see it described that way, like in a science class, for example. Okay, so let's just do one quick example. Let's actually take this backwards. Let's say I have 2 spheres. And I'm going to tell you that the volumes, let's say the volume ratio is, let's say it's 27. I'm going to make this kind of nice numbers as it turns out. 27 to 512. You might think, wow, those are kind of random. Okay. And I would like to know the surface area ratio. I would also like to know the circumference ratio. Because I can still measure, let me sort of highlight that in purple maybe. I can still measure one-dimensional things, like what is the circumference of the equator? So the circumference of a sphere, by definition, is just the circumference of any great circle like that equator. That's a length measurement. So that's a length, that's an area, that's a volume measurement. I'm giving the volume ratio. Well, that should be the cube of the most fundamental ratio, which is the length ratio. And luckily enough, 27, if you take the cube root of that, it's going to be 3. If you take the cube root of 512, that's actually 8. So in fact, the circumference ratio is a 3 to 8 ratio. And so between twice and 3 times the circumference. The surface area ratio, that's going to be a squared to b squared. And that's going to be a 9 to 64 ratio. Oh, if you break that out, it's about a 1 to 7 ratio. Okay, so this is the simplest, the sort of smallest ratio. This is between 2 to 1 and 3 to 1. This is about a 7 to 1 ratio. And this is about a 20 to 1 ratio, maybe not quite as much. And that's because volume comparisons are always going to be more extreme. Remember, like here, if I triple a length in a cube, I make areas 9 times bigger, definitely a more extreme comparison, but I make the volume 27 times bigger from a measly tripling of one of the dimensions. That's really important just for basic intuition. Whatever the length ratio is, you're going to get a significantly bigger area ratio and a much, much bigger volume ratio because you can fit a lot of cubes inside this bigger cube. Okay.